Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome back to The Deep Dive. We grab complex source materials, simplify them, and give you knowledge you can use right away. Today, we're really focusing on something fundamental for flying, the altimeter. Absolutely vital stuff, especially if you're a student pilot gunning for that license.
Oh, absolutely. It's the cornerstone of vertical safety. You look at it, you see a gauge, but it's really a highly sensitive barometer.
Yep.
It's measuring atmospheric pressure constantly, turning the weight of that air column above you into feet.
And the air's always changing, right?
Exactly. It's never static. So how we read that instrument needs to be just as dynamic.
Okay, let's get into this then. Our mission today, decode the altimeter. We'll cover how to set it right, the serious risks of getting it wrong, and we'll really nail down those 5 types of altitude every pilot just has to know.
Think of it like this. The altimeter speaks the language of pressure. If you don't understand that language, you genuinely don't know how high you are.
Right. Let's start with the instrument itself. Looking at it, you see the hands, obviously, but there's that little window, the Colesman window.
Yes, the Colesman window. That's your barometric pressure setting window. And there's usually a knob, often near the bottom, that you use to adjust the number you see in that window.
That knob connects you to the ground conditions, essentially.
Precisely. It lets you calibrate the instrument to match the local atmospheric pressure reported from an official source, like an airport. Now, the scale in that window, it's usually in inches of mercury you'll see Hg, but sometimes you might see millibars, mm, as well.
And the number we're dialing in, what does it actually represent?
Good question. It's defined as the station pressure. That's the real pressure measured at the weather station, but then mathematically adjusted as if that station were at sea level.
Okay, so it standardizes it to sea level. But here's the part that often catches new pilots out, isn't it? That setting is only really accurate right near the station that reported it.
That's the critical takeaway. You fly, say, 50 miles, 100 miles away, the weather system, the pressure, it's likely different. You absolutely must assume the atmosphere has changed, and you need to update your altimeter setting as you fly from one reporting area to the next.
So how do you get those updates mid-flight? If you're talking to air traffic control, ATC, they'll tell you.
Yep, ATC is your primary source if you're working with them. They'll give you the new setting when you enter their airspace or as conditions change. If you're flying VFR on your own, not talking to ATC,
then it's on you.
Completely. You need to be tuning in to automated systems. That means listening to ADWOS Automated Weather Observing System or ASOS Automated Surface Observing System broadcasts, or at bigger airports, the AT, the Automatic Terminal Information Service. You have to actively seek out that number.
It's interesting, though, this expectation versus reality. We dial in the number, we think, okay, that's my exact height, but it's not quite perfect, is it?
Not entirely, no. The setting corrects the pressure at the station down to sea level, but it doesn't, and really can't, account for every atmospheric variation, especially higher up. The big one is non-standard temperature. If it's way hotter or colder than the standard atmospheric model predicts for that altitude, the altimeter reading will drift a bit.
So if it's not perfectly accurate, why rely on it so heavily?
Because the primary safety goal here is relative separation. If every single pilot flying in the same chunk of sky uses the exact same altimeter setting, even if it's slightly off in absolute terms due to temperature, their instruments should all be affected by that error in the same way.
Ah, okay. So everyone's altimeter might be reading a little high or a little low, but they're all reading high or low by the same amount relative to each other.
You got it. That maintains the vertical separation between aircraft. It keeps planes apart vertically.
But, and this is crucial, it doesn't automatically guarantee you'll clear a mountain peak.
Precisely. Maintaining that separation is key, but it's not a substitute for knowing your terrain clearance. That's why meticulous flight planning and always keeping a sharp visual scan outside the cockpit remain absolutely non-negotiable. The altimeter helps keep planes apart, but you, the pilot, keep the plane away from the ground.
Okay, let's make this real. Let's walk through a scenario showing how even a tiny error in that setting can have huge consequences. Say we're flying west from Dallas Love Field towards Abilene.
Perfect example. This really highlights how a small fraction of an inch on that dial translates into potentially hundreds of feet near the ground.
So we take off from Dallas, Set the altimeter to, let's say, 29.85 inches of mercury. We glance at the altimeter and check it against the known field elevation, 487 feet. Looks good. We fly along.
Maybe an hour into the flight, ATC, or we pick up a new setting from a station midway, say 29.94, we dial it in. Standard procedure.
Right. Now we're getting close to Abilene Municipal. Field elevation there is 1,791 feet. We want to fly the traffic pattern at 800 feet above the ground, AGL.
Okay, so simple math. 1,791 feet elevation plus 800 feet pattern height means our target indicated altitude on the altimeter should be 2,600 feet.
But maybe things get busy. Pre-landing checks, radio calls, and the pilot forgets. They fail to update the altimeter from that mid-flight 29.94 setting to the actual current Abilene setting, which let's say is lower, maybe 29.69 inches of mercury.
Okay, now we have a problem. The difference between the setting in the window, 29.94, and the actual pressure, 29.69, is 0.25 inches of mercury.
And the rule of thumb, about 1,000 feet of altitude change for every 1 inch of pressure change?
Roughly, yes. So 0.25 inches times 1,000 feet per inch, that gives us a 250-foot error.
And which way does the error go?
This is the critical part. The pilot thinks they're entering the pattern at 2,600 feet indicated, but because they have a higher pressure setting dialed in than reality, the aircraft is actually flying approximately 250 feet lower than the proper pattern altitude.
Wow. So they think they're at 2,600, but they're really at 2,350 feet.
Exactly. And when they land, if they hadn't corrected it, the altimeter would show about 250 feet above the actual field elevation. It would read 250 feet when parked on the ramp.
Hold on, though. If the main point of everyone using the same setting is separation, and this pilot is just 250 feet low, if everyone else in the pattern is set correctly to 29.69, are they really in danger of hitting another plane? Isn't the separation margin still okay?
That's a really important clarification. You're right. The immediate danger might not be hitting other traffic that's correctly set. The problem is the terrain. By being 250 feet lower than indicated, you've just slashed your safety margin over any obstacles in the traffic pattern area, like radio towers, buildings, rising ground. Especially if visibility isn't great.
So the error relative to other correctly set planes might be manageable, but the error relative to the ground is suddenly dangerous.
Precisely. That's why terrain and obstacle clearance is always paramount near airports. And it leads to that vital memory aid every student pilot needs. Low to low. If the actual pressure, like Abilene's 29.69, is lower than what you have set in the Colesman window, the incorrect 29.94, then your actual altitude is lower than what your altimeter indicates. You set it too high, the plane is too low.
Got it. High setting means low flying relative to indicated. And this gets even worse in mountains, right?
Exponentially worse. In mountainous regions, strong winds, mountain waves, and dramatic temperature variations can cause massive pressure fluctuations. Your altimeter could easily indicate 1,000 feet or even more higher than your true altitude above sea level.
So you might think you're clearing a ridge by a comfortable 500 feet, according to the dial.
When in reality, you're barely skimming the trees, or worse. You absolutely must build in a very generous buffer when flying near high terrain, not just for potential altimeter errors, but also for unpredictable things like strong downdrafts. Don't trust the minimums.
Okay, this really underscores why understanding the nuances is so vital, which brings us to the language itself. We keep saying altitude, but as we've seen, it's not just one thing. There are different types, right? 5 key ones.
That's right. 5 essential types every pilot needs to have crystal clear in their head. We can sort of group them. One's you see and use for navigation, and one's used more for performance calculations.
Let's start with the basics. Number 1.
Indicated altitude. This is simply the number you read directly off the altimeter face after you've correctly set the current local altimeter setting in the Colesman window. It's uncorrected for temperature errors. This is the altitude you'd report to ATC if they ask.
Okay, straight off the dial. Number 2.
True altitude. This is your actual real vertical height above mean sea level MSL. This is the benchmark. It's the altitude used on all aeronautical charts to show terrain elevations, obstacle heights like towers, and the vertical boundaries of airspace. It's the official height.
So true altitude is fixed, like map data, but then there's absolute altitude that changes constantly as you fly over uneven ground.
Exactly. Number 3 is absolute altitude. This is your height directly above the ground immediately beneath your aircraft. Above ground level, or AGL. Picture flying level across a deep canyon. Your true altitude, MSL, stays the same, but your absolute altitude, AGL, increases dramatically as the canyon floor drops away, then decreases as you cross the far rim.
Makes sense. Indicated, true, absolute. Now, the one's more tied to how the plane performs. Number 4 is pressure altitude.
Right. Pressure altitude. This one's crucial for performance calculations. You find it by setting a specific standardized pressure in the Colesman window, 29.92 inches of mercury.
Why 29.92? Why that specific value?
It represents the internationally agreed upon standard atmospheric pressure at sea level. By everyone setting 29.92, especially aircraft flying at high altitude, specifically above 18,000 feet in the U.S., known as the flight levels, they're all referencing the exact same pressure surface in the sky, regardless of the actual weather far below.
So it creates a universal reference plane way up high for guaranteed separation, independent of local weather.
Precisely. It ensures consistent vertical separation in the upper atmosphere. And critically, pressure altitude is the starting point for calculating things like true airspeed and, importantly, our next type of altitude.
Which is number 5, and arguably the most critical for takeoff and landing safety, especially on hot days. Density altitude, or DA?
Yes, density altitude. This is simply pressure altitude corrected for any deviation from standard temperature. And this is fundamentally important because the density of the air dictates almost everything about your aircraft's performance.
How so?
Think about it. Air density affects how much power your engine can produce. Less dense air means less oxygen for combustion and normally aspirated engines. It also affects how much lift your wings generate. Less dense air provides less stuff for the airfoil to push against.
So lower density means the engine makes less power, the wings make less lift, the plane feels sluggish.
Exactly. It feels sluggish, it accelerates much more slowly, and crucially, it needs a lot more runway to get airborne. Let's use that example from the sources. Airport elevation, 5,048 feet MSL. On a standard temperature day for that altitude, say 5 degrees Celsius, the density altitude is the same as the elevation, 5,048 feet. Performance is as expected from the charts.
But take a hot summer afternoon, temperature climbs to 30 degrees Celsius. That's way above standard for 5,000 feet.
Right. The air expands, becomes much less dense, and the density altitude shoots up. In this example, it jumps to 7,855 feet.
Wow. So even though the airport sign says 5,048 feet, your airplane performs as if it's taking off from an airport at nearly 8,000 feet on a standard day?
That's exactly it. You'll need significantly more runway. Your climb rate after takeoff will be much weaker. It's a huge safety factor. Now, flip side, very cold day, say minus 25 Celsius. The air is super dense. The DA plummets, maybe down to 12,232 feet in the example.
And the plane feels like a rocket.
Pretty much. Takeoff performance is crisp, climb is strong. The takeaway is you must calculate or at least consider density altitude before every single takeoff, especially from high elevation airports or on hot days. It directly impacts your safety margins.
Understood. Okay, quickly then, let's recap the mechanics. The pointers move because of pressure changes expanding or contracting those little metal discs inside the aneroid wafers.
Correct. That's how it senses altitude changes. But remember, the pointers also move when we turn the knob to change the Colesman window setting. That mechanically shifts the linkage.
And that leads to that interesting overnight checks scenario.
Right. If your plane is parked, tied down, and a low-pressure system moves in overnight, say the pressure drops from 29.98 down to 29.68 inches of mercury.
The altimeter thinks it's climbing.
Yep, that 0.30-inch pressure drop will be interpreted by the instrument as a climb. It'll indicate roughly 300 feet higher than it did the evening before, even though the plane hasn't moved an inch. It climbed while sitting on the ramp.
Which perfectly illustrates why the pre-flight check of the altimeter is so vital. Every single flight. What are the steps again?
Simple but critical. Step 1. Get the current official altimeter setting for the airport from ATC, ATIS, AWS, ASOS, or flight service. Step 2. Carefully dial that exact number into the Colesman window.
And step 3, the most important check.
Compare the altitude now shown by the pointers to the known published field elevation of the airport. They should match or be very close.
And how close is close enough? There's a tolerance, isn't there?
There is. The rule is, if the indicated altitude is off by more than 75 feet from the surveyed field elevation, that instrument is considered unreliable for flight.
Why 75 feet specifically? What's magical about that number?
It's not magic, it's engineering and safety standards.
Yeah.
75 feet represents the maximum allowable cumulative error from mechanical friction, lag, and inaccuracies within the aneroid system itself at ground level. Any error bigger than that suggests a potential fault that could become much worse at altitude, compromising the precision needed for safe vertical separation, especially in instrument conditions or busy airspace. It's the mandatory limit to ensure the instrument is trustworthy.
So if it's off by more than 75 feet,
it needs to be checked and potentially repaired by a certified instrument technician before the aircraft flies again. no exceptions. So wrapping it up, the core safety message here is crystal clear. Knowing your true altitude is absolutely vital, not just for staying separated from other aircraft, but critically for ensuring you clear terrain and obstacles, especially when you can't see them clearly.
And for the student pilot listening, the big takeaway really is the altimeter isn't passive. It demands your constant attention and action to keep it synchronized with the ever-changing atmosphere. It's definitely not a set it and forget its instrument. You're actively managing it throughout the flight. Which leaves us with a final thought for you to ponder. We've established that setting the altimeter correctly is key for vertical separation within the air traffic system. But imagine you're flying under basic VFR, clear day, no ATC services. Which of those 5 types of altitude indicated true, absolute pressure, or density would you be paying the most attention to for immediate terrain clearance right below you? And how might your focus shift the instant you contact ATC and enter controlled airspace? Something to think about.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.